We this is the first talk in our online seminar series this academic year. We just started here in Seattle. This online seminar has been going since 2015, long before the pandemic. Of course, during the pandemic, this was a very convenient vehicle to continue these scientific endeavors, and of course, many other online seminars started. Even though I think a lot of places are going back to regular seminars, we will definitely continue this one for the time being, and probably later. And so this first speaker for academic year 21-22 is Richard Kollár. I've known Richard for quite a while. Richard got his PhD from Carnegie Mellon University under the direction of Bob Pagel. And Richard, I may skip a postdoc here. Then he went to Michigan, where he worked with Peter Miller. And since then, he's been at Comenius University in Bratislava, Slovakia, where I've had the pleasure of visiting him. When I invited him to give a talk in this online partial differential equation series, he told me he had nothing to say about applied PDEs because he'd been working on the pandemic. And then, I told him that lots of people would be very interested in hearing about that. And I think the size of the audience is speaking to that. And so I think we're all excited to hear Richard talk about what he's done about this. Thank you very much, Richard.
So thank you, Bernard, for the introduction and for the invitation. So this is really unusual story for me. Today, we had our first seminar after 2 years at our university. So it's a really special day for the seminars, at least for me. As Bernard said, I used to work in nonlinear waves, and I still working in stability problems and related stuff. On the other hand, I always had this partial interest in applied mathematics in biology. So I worked on a couple of projects, and that some way got me involved in pandemic, or the dynamics of pandemic and modeling of the pandemic data. But this is some unusual story because I started as somebody who was commenting and helping to develop the models, but some way the fate turned out to be very different, and now I'm really one of the most famous people in Slovakia, and it's a really crazy thing because I just become part of the media coverage of the pandemics in our country and also in other countries. Partially, I was interviewed by many other media, and now it's very usual that I'm, in the main news, almost daily, and featured in many newspapers. So some way it changed the way I'm looking at some things, but I'm looking, forward to some way go back to mathematics and to really pure mathematics. So today, what I'm going to talk about is about 3 lessons I have learned. I'm saying we have learned because I know more people who actually have the same lesson, but something I didn't know before and learned about the dynamics of epidemics over the last 2 years. So this is joint work with 2 papers are joint work with my wife, Katarina Bodová, and at the end I will work about the diploma thesis of my students, Kamila Horvátová, who finished last semester and now is somewhere in the business. I don't know exactly where. So 3 lessons, and here is just a short overview of these 3 lessons. One of them is that the compartment-based models we usually, teach students as a great example of how applied mathematics works. They need to account for the effects of testing, especially during these pandemics. Okay, it may be obvious, but I will show you that, and you will see that it's really not that easy. And real data actually show an apparent algebraic decay of the effective reproduction number. You probably all know what's effective reproduction number. I will explain it in some detail. But some way this is something unexpected and something which is not easy to interpret. The second thing I will talk about is more related to the partial differential equations, although it won't have any equations almost. But I will show about the long-range exponential trends in the pandemic data. So something which actually may tell us or give us some idea about how the models should be constructed. Also, I will show that the test positivity itself is exponentially distributed, or it was distributed in some type of data. And then I will show something about the characteristic spatial scales, especially characteristic spatial scale of test positivity, and it's about 10 kilometers. So in some way says that in a circle of radius 10 kilometers, you have the highest probability that the situation is some way homogeneous. If you go further, it's like bending of the cable. So this is the elementary part, which some way doesn't bend that much. 10 kilometers should have a really high level of correlation. And the last point I want to make, hopefully I will have time for that, is that the concept of herd immunity needs to be revisited seriously. And yeah, I will explain why. I will use network models for that. So that's the part of the diploma thesis of my student. The first parts are already in the published papers. So if anybody is interested, I can provide the references. So here is the situation in Slovakia right now, and it's just okay. Doesn't matter, right? But it's just showing us, what's the situation where we are right now, and you see the end. These are the daily new cases, so this is the incidence, and you see this growing wave coming. So actually, we are, things are really getting worse, seriously worse. Many of the hospitals are overcrowded now in Slovakia, and yeah, I got call today from a couple of people. First of them was that they don't have enough medical personnel in some of the hospitals. The other was that we will have the same problem in the social services housing. So yeah, things are really, some way very acute and very emerging, I would say. So but just to compare the situation with your situation in state of Washington or in the world, somewhere in the world, this pandemic wave is, is going down. Of course, the reason is that the situation in Asia, in the highest populated countries, it's becoming better. So Europe, which is partially growing, or in Eastern Europe, which grows now, doesn't matter that much. So that's a good news for the world, and hopefully this is the last big peak, and we won't see more. I'm not going to comment that much on it, but maybe some of it. And state Washington is some way following the world trend. But you see the story in Washington was some way similar to that of Slovakia. Okay, a little bit different, a little bit more waves, but yeah, still, the end. At least right now, you're looking at a better perspective clearly. So that's a good news. So the lesson one I'm going to talk about is the algebraic transient data and algebraic decay of effective reproduction number. So this is just the illustrative picture. I will get to it. So I will talk about very simple models, something we, probably most of you were teaching at some point. So this is the simple SIR models where you have susceptible, infectious, and recovered. And I'm really not going to explain it. I would feel bad if I have if I went the details. But this is really the most celebrated model in the epidemiology, at least. So what matters more is that there's this concept of growth or decay of the number of infected people. So that's the second equation, which is in the top in this frame, in the red frame. And what you see is that when you factor gamma and I, it's just some kind of exponential growth, and the factor, whether it's positive or negative, will determine whether the number of infected people will grow or decrease. And at the early epidemics, when susceptible is equal to 1, so this is already normalized by the population. So if almost everybody is susceptible, so then the expression beta S over gamma has the value beta over gamma, and if beta over gamma is bigger than 1, so then I grows, and then the epidemic some way starts. And if beta over gamma is less than 1, then the epidemic somewhere decreases. So, or number of infected decreases. Epidemic doesn't typically start, at least in this deterministic model. So we call this number beta over gamma the basic reproduction number, and that number should characterize the property of the pandemics, or of the epidemics. So, and these are parameters in the ODE models. Beta is a number, gamma is a number, and we work with those. Here are the typical numbers or typical reproduction numbers of the diseases which we recognize, transmission diseases, and you see the measles are really leading the chart by 12 to 18 value. This is really pretty high. we have no idea how measles are fast, once they, outbreak happens. So pertussis happens, quite often as well, and it has some similar characteristic as a number. So, but then it's a jump to like smallpox, polio, and rubella, and I don't know, even the diphtheria. I don't know even know what's the disease, but so some way, so these reproduction numbers are substantially lower, and then influenza and HIV and SARS, the original SARS, are in much lower bracket for reproduction number. The original corona from China, in some way it's was estimated with the reproduction number somewhere between 2.5 and 3, so it was not that infectious. On the other hand, the Delta right now maybe somewhere around 8, but it's a basic reproduction number. Only if the whole population would be susceptible, that would be really fast, but that's not the case at all. So so that some way give you some idea where we are. But what matters more during the duration of the pandemics is not the basic reproduction number, but the effective reproduction number. This effective reproduction. Okay, there should be reproduction number there. So so that's R of t doesn't have S equal 1 because the whole population is not anymore susceptible, and it's really the ratio beta S over gamma which determines whether you locally in time grow or decrease or decay. So that's the number which is often reported, but has also a lot of weaknesses, a lot of misinterpretations. The problem is that this is too oversimplified, and now I'm going to address little problems, or what problems actually this model may have, and so on. So, but the first of all, thinking about any of these parameters as a constant, that's pretty difficult. Beta and gamma are the parameters, but this gamma, in fact, should some way correspond to the average time of infectiousness. So it's the time during which the mean time during which the person spent spends in the compartment with in infectious compartment. So it can infect the others. So gamma is it's 1 over t, where t is the infection, the average time. So, and here are some data. You have plenty of data. This pandemics creates vast amount of data, and this is some of them. So these are just individual records of people who get positive and negative tests. The black, each row represents one person, and these are the consecutive tests of each person during some time during March, and from March to May of the last year. So this is early pandemics, and you can see that people have a positive test first. They enter the data, the database, and then they have plenty of negative tests. But it's looking like plenty, but each of them only needs 2, and after 2 positive tests, 2 negative tests, that person was some way freed from the quarantine and could go on. So at that time, we got plenty of tests of individuals. So this provides some idea, at least, about the early type of virus or every strain of virus, about how the infectious time was distributed. But of course, we know the limitations of PCR testing and all of that. That doesn't mean the positive test doesn't necessarily mean the person is infectious. But anyway, it gives you some glance at how long a person can be identified as infectious or infected, better to say. So, but even this gives you distribution, which is a little bit crazy. So if you look at it, that's just a summary of the data on the previous picture, and it shows that many people are infectious 14 days. That's some way the peak. But the funny thing is, it doesn't really mean people are really infectious 14 days. So this is a huge limitation, because in fact, in the government policy in Slovakia was that you couldn't get tested earlier than 14 days after getting infected, the first positive test. So this data, probably would have this peak at 14 would have it somewhere, in the lower numbers, because many people would have a negative test earlier. But so that's the first thing. So the data are not real data. There's a lot of influence of the strategies and testing testing routines and so on. So the data are not what you want. It doesn't provide you the information you need. Of course, the data are a little bit better, later on, and we see many people with really long time. We know now that it may be delayed viral shedding. It doesn't need to be related to necessary to infectiousness. But anyway, this is just showing you how the data look like and how many limitations they have. But in this ODE, simple ODE model, we're thinking, oh, there's some mean value, and we replace gamma by mean value 1/t, where t is the mean value of this distribution. Of course, it's not going to behave completely perfectly, and it doesn't need to even provide the right information. So when you plug in, there's one, simple consequence I learned very early in this pandemic, that if you plug in this gamma is 1/t, then this effective reproduction number is beta times s times t. And this gives you some interpretation of what's happening. So when you're thinking, when you want to, some way improve the pandemic situation in your location, then you really need to some way improve this product of beta times s times t. Of course, it's not going to be that, but in general, these are the factors, and it's not the individual factor, it's the product of them. So decreasing any of them by, say, half should be approximately of the same level of effect. So beta is related to contacts and face masks and hygiene and home offices and closed dorms and so on. So beta is something which usually we put our measures, pandemic measures, to limit beta. On the other hand, S is the number of susceptible people in the population. Typically, of course, during the pandemics, the S is decreasing because more people getting infected and they're getting some kind of immune response. So that's actually improves its vaccination, also not only by getting infected, but also by vaccination. And also isolation of healthy people for a while may decrease S. But a lot of usually we work with B and S, but the very important is also the T, the one I showed you, and contact tracing is actually improving the T significantly. If you can decrease the time people spend outdoors infecting others by half, then actually it has the same effect as many other pandemic measures. And also deaths, of course, are shortening T. If people are dying faster, that actually decreases T as well. But okay, so this is just really early thing, and this is not a lesson yet. Don't really worry about it. This is just a simple observation, but not often seen. So, but I have really a problem. There are many problems with this model, SCR model, and from the perspective of a mathematician, I would be really concerned with the following things. First of all, the pandemics is approximated by a continuous process. In general, it is not. So it has a stochastic nature, and it works with integer arithmetic typically instead of real arithmetic. And also, this model actually is not performing very well and very realistically at small values. So these are like some mathematical objections, which typically when I was teaching this, I was explaining why these problems are relevant and how they may fail. But it seems like this is very minor because there are much more important problems with the model in general, which are not that easy to fix within even wider scale of compartment-based models. First of all, it some way works with constant population, but there are not growth, the births and deaths which matters, but it's import. So people traveling from other places, and that's not easy. How you model that? There are some ways how you do it, but it also depends on what the situation in the other country. Suddenly, in other places, you need to really, some way, the model somewhere explodes in number of factors you need to consider. Also, it some way has these identical individuals. Of course, you can introduce many groups, but that's not easy. Typically, people do not have very similar behavior, at least from the standpoint of pandemics. It turns out that individual properties, like how much people individual can shed off the virus when speaking, matter, and that actually makes the problem very difficult. Also, the homogeneous population is not just identical individuals, but also the homogeneous population makes the trouble. In general, actually, you're really interacting with a network of people, and so that's another complications. And of course, this constant transfer coefficients, this beta and gamma, they changing in time. Because you're changing the measures and so on. So this is very difficult, and anybody who is actually doing pandemic modeling I really respect them because they need to deal with all these troubles, and it's not easy. It's not easy to get anything meaningful if you don't resolve all these issues to some extent. But this is not the end. Of course, there are other problems which I call minor from the modeling perspective. Is the difference between recovery and death. Okay, that's easy to some way take care of. There's also this incubation period. Okay, that's typically really easy to take care of as well, but not necessary because we don't know exactly this incubation period. The behavior of people may change. Not easy. Some people. And also the infection time distribution is it's again something we do not know that much. We know now more than we knew at the beginning of the pandemics, but still. So some way I consider this, 5 points, on the top: the identical individuals, homogeneous population, constant transfer coefficients, constant population, and also to some extent this infection time distribution as serious problems. Maybe the yellow one is not that difficult to take care of, but the first 4 are really making it complicated. So once you realize that, you understand that modeling of pandemics is a difficult job. So IHME at Washington, they did a really good job, but it's not easy for them, and they fail to predict things many times just because they didn't have that the general model couldn't have detailed information about what's going on in many places in the world. So for Slovakia, we had this model of Ministry of Health. That model was really not very, I would say, complicated originally, but some way they let me to advise them, and we end up with pretty complicated stuff, which some way takes into account the age categories, inter-age contact matrices, and also we had the access to mobility data, so we knew how many people are going from place A to B every day. So we based on the data we had, we set up a model which is the closest I will get today to the PDEs, because this is a discretization of a pretty complicated PDE, of course, because we have a mobility in between the nodes. These are individual villages or individual villages are cities in the country, and we have these different age groups, and they moving and they interacting. Okay, that model some way worked, but of course we fitted it to the data, available data, and we know the limitations of the data. They do not really report the number of infected people. We still don't know how many people were infected in this pandemic. So if we knew it, it would be really much easier. So, okay, you can run some scenarios and so on, but you never get the satisfaction that something really works. Because if you are matching the data, then you typically are wrong, because the model assumptions are not those which are some way corresponding to the data reported. So we some way came up. So this model produced some scenario early in 2020. It was done I think in April 2020, when there was this huge hype of the models. And we produced this long wave and huge wave, which some way predicted that things will be bad for a long time. But it's not the prediction, is the scenario if the R0 would be 1.1. I mean, after reduction by the measures. The red one matters. The lower ones were some optimistic scenario. But as I showed you originally, the curves of the pandemics was very different. And what we were predicting was this wave in April 2020. You cannot even see it. We didn't have the pandemics that time. We thought we have, but there was nothing happening. It was like, when we look at it now, it was like really zero. We were the country which started with lockdown right away. We started lockdown even before we had the first death. So nothing happened really. But of course, the model didn't, model that situation. And when you look at it, some way, okay, we see a couple of peaks, some way in the confidence interval, we just followed it. Of course, there's a completely random connection that has nothing to do with it. We didn't, model that that situation. And I'm just saying, in these models, you are getting, some curves, but whether they really correspond to what you see, it's very hard. And, even if they match, doesn't mean anything. Because it doesn't give you the understanding. So that's the start of my getting me getting involved with this. I got really frustrated because I understood there's just no way we can really improve the models that much, because we don't have the data to calibrate the models. and that's very difficult. Maybe the situation somewhere else was better. The data we had for our country, there was just no way we could predict anything. So, but it turned out that me and my wife, we had a prediction 1 month ahead, perfect prediction of our wave, of our spring wave, the one you don't see. Okay, it has some, it's that time we thought it's a lot of people, but we had just perfect prediction at the time when these SIR models were predicting the tens of thousands, hundreds of thousands of infected people. We came up with prediction that we will have 1,000 people at the top. We predicted the date, which was off by a couple of days, and it worked very well. So I'm just showing you that sometimes just looking at the data without actually understanding what the data mean may work. And that's, for me, it's the really opposite way I was thinking about problems before. I always try to get understanding and build it, not to look at the data itself, but some way it worked in this case. So first of all, this what I'm going to show you are active cases which were reported at the time. Again, this is the first pandemic wave. And, if you plot it on the log scale, you see exponential growth. This is Afghanistan and Bolivia and so on. But Afghanistan and Bolivia at the time were exceptions. Of course, initially you expected in the compartment-based models, typically you see approximately exponential growth, but surprisingly, actually what we were seeing in the data in many countries like Argentina, Indonesia, but more countries were more like algebraic growth, so power law growth. And so on the log scale, which you have on the right always, and on the left is the semi-logarithmic scale, you see that the growth is algebraic. And it's not just those two countries, but it happened in many countries. We saw it across many countries, Somalia and Russia as well. And at the time, I came across of a paper by Robert Ziff from University of Washington, who modeled the number of deaths in China. And he was working with this setting of Vasquez from 2006, when he was looking at age-dependent branching processes. And he saw the polynomial growth, so some kind of parallel growth over here in time, but also has the decaying exponential. So this is pretty far from what SIR models will give you. But as you see on this picture, on this example here is the data from Czech Republic. The green line is exactly this curve, which was fitted, by, not exactly this form, but some different form was fitted to the data. And you see the agreement is pretty, amazing for Czech Republic. If it was for Czech Republic, that would be not enough. But the fit was good almost for every country in the world. Of course, the parameters TG, alpha, and A are different for those countries, but the fit was some way good. And typically, the fit was pretty good after the country some way introduced really strong measures. So some way this worked, miraculously. And here are a couple of pictures which show you a couple of countries. I don't see the top one, but it's Canada, Hungary, Netherlands, and you see, after the initial transient, you are some way following this green path pretty well. Of course, this may be just account for fitting, but it works for almost everybody. So that was the fantastic thing. It worked for Andorra, Austria, Australia, Croatia, and these countries are there just because they're starting the alphabet. Okay, so it just goes almost everywhere. Of course, it's not perfect, but it really simulates the data very well. It actually turned out it's good for modeling of one pandemic wave, although in the next wave it was not in every country. Some way the wave it started to play with the measures, pandemic measures, the governments. So it changed, and you can if the measures are changed too often, you can change some way the shape of the curve. But this is something really weird, isn't it? Because it says that regardless of the way countries are reporting numbers, because there are huge differences, and regardless of the level of testing, that's really important. The level of testing is very different in different countries. Nevertheless, you see similar curves across many countries. Of course, you can go in alphabet further, and it just goes. It's just 2 or 3 parameter regime. It's incredible. So some way, I was really surprised. It works so well, but it was always possible to do some prediction based on it. Of course, it's not perfect because the next wave may be coming afterward, and as you can see over here, it's easy to divert from that course. And the model, this is not model which has no understanding of the data. It doesn't explain you why you're going, away. So yeah, so it has some limitations, definitely very serious limitations, and you cannot predict anything. You can just tell that once you have the wave, and if things go fine, then the wave, what will be the shape of the wave. And here is a real interesting thing. So it fits the data. And if you look at what differential equation this number of infected satisfy, it's this equation. And if you calculate what it means for the reproduction number, it says that the reproduction number during this period, during this time, close to the peak of the wave and before and afterward, is decaying algebraically as 1/t. So that means beta times S over gamma, and its population, size of the population that's not involved that much. So beta over gamma times S some way decay algebraically as 1/t in the data. Why this is so, I have no idea. Yeah, it's definitely not the number of susceptible. If that was 1/t, that would be great, but that's not happening for sure. So it must be that the beta and gamma, and also something you don't see here is the testing level. So it's some way saying that the countries are adjusting the testing levels so that it fails into this framework. It's so weird. So yeah, I have no explanation. There are some theoretical models that spreading in 2 dimensions and so on. There are some models which explain why you should expect some kind of algebraic decay, but why this is so, when you have such a difference across so many countries, I have no idea. And but that's how it is. So also we used it for prediction, and we had this prediction tool which worked online and was pretty solid, at least during this first wave. Again, the second wave, when the the pandemic measures differed too much, and not just across the countries, I don't care about that, but it was more that the countries were changing the measures according to the pandemic state. So that really that introduced many small wiggles. And that was not exactly didn't fit very well into this framework. So we wrote this paper about it, and I felt, okay, I don't understand what's happening, but okay, it just raises questions I may address sometimes later. But then in the fall of last year, approximately a year ago, our prime minister came with this great idea that we will be the first country in the world that we will do mass antigen testing in Slovakia, and we had it. We tested over one weekend, more than 60% of the population over one weekend. It was not the self-home tests or whatever. You had to go to this testing station and take the test over there. Whatever I'm feeling, thinking about it doesn't matter right now. I just want to show you what data we collected. We have actually, our government published a paper in Science, which actually says how this antigen testing was great and how it worked fantastically. Unfortunately, Slovakia, just shortly after this antigen testing, became the country from month with the highest number of deaths in the world per capita. So it's really a bit suspicious, and I'm not sure about the success. But what I want to really show you really are the outcomes. These are great data. Look at this picture. So we have for each individual municipality in Slovakia, we have this positivity of the tests on that day, on the same day, and a huge, in the high enough level of population. So these are fantastic spatial data, and maybe tell us something about the properties of, how spatially distributed are the infections, at least at one moment at time. So these was the first round of the testing. Then in a week we repeated the testing, but only in the regions which were worse in the first round. So I think half of the country was tested again, and you see the results again. And finally, in 2 weeks later, we had the third round, but not now in the half of the country, but only in those municipalities which were mostly affected in the first and second round. So these are just a couple of municipalities. So anyway, so what have we learned? So this is really interesting, and I really love this data because they really show something interesting. So first of all, we look at just the pure distribution of the positivity of the test in individual municipalities. We had 5,000 municipalities in round one, and we look how they are distributed. How the distribution function look like, and that's the blue triangles you see. And this is the semi-logarithmic plot. So it's fantastic exponential distribution. Wow, so I was amazed, but it worked also in the second round, which was amazing, and also in the third round, where you need to clear the data of the non-residents, because that time the testing was only in few municipalities, and many non-residents were tested in those municipalities. So you need to clear clean the data. So some way it shows you that there's some kind of exponential phenomena there, which tells you that they are exponentially distributed. So if anybody, is thinking about the spatial model, this should be somewhere part of it, at least with antigen tests. But we also see some other exponential distributions or exponential trends. Some of them is that if you look at the relative change of the positivity between the rounds, and if you again look at the histogram, again it looks like it's exponentially distributed. That's really interesting. So that's the black squares that show the difference between first and second round. Okay, the first and second, the green circles, they don't look that so perfect, but from the first to second round, we also see some exponential improvement. So very interesting. It also showed that there are huge number of municipalities. These are all the black squares which are beyond the red line. Actually, the second round was worse than the first round. Okay, but they are, this is exponential, don't forget. So the one or two squares on the top are some way most of the municipalities. Anyway, so exponential trends, but how they may appear. So that's the question. So again, we have this fantastic data and spatial data. We didn't use the spatial structure yet. So first of all, we looked at something which we call the characteristic scale. So when you look at it, you want to know on what scale the data are correlated, and if it's a too small scale, then the randomness shows up. But if you are too far, then the differences between the regions show up. And that's what we see. We're looking at the statistics, which is called Moore and Global I statistics. It's some kind of correlation when you're looking at, you define what neighborhood means, and then you're looking whether the neighborhoods are actually some way correlated. And we made the neighborhoods by define the neighborhoods in 3 different ways: the blue, red, and yellow picture in the middle. And we see that the maximum of this spatial correlation happens at the same distance, about 10 kilometers. Okay, here are some other local maxima, but yeah, it seems like this 10 kilometers is really a well-defined scale in the problem. So it says that the maximum correlation in the test outcomes really comes on the spatial scale, 10 kilometers. Okay, so that maybe may advise to some measures you may think about in the future. Yeah, this was it. And the last thing I about this mass testing is that we want to actually see whether there are some kind of trends, spatial trends in the data, but it's very complicated because you see convolution of different sources, and you want to identify each of them. You may look at them locally. Locally, you see some patterns, but you want to see some global patterns, whether something happens on the longer time, spatial scales. So we did this calculation when we take this map. This is Slovakia, and we use some diffusion just to show the picture. We didn't use it with the data, just to visualize better. And so that's the PDE. Okay, I have a PDE over here because this picture was obtained by a diffusion equation. Okay, at least something. Okay, I'm glad. But we look at 9 focal points. We call it southwest, west, northwest, northeast, in the corners and in the center. And from each of these points, we made these concentric annular regions, and we calculated the average positivity of the test in each of these annular regions. And we look, how it looks like from this point of view. And the yellow star in the middle somewhere refers to that was the area of the highest positivity in Slovakia. So that will be the reference point. And we will some way put equal all those pictures, with this with respect to this reference point. And here are the outcomes. And especially, I want you to look at the top one. So over here, you see that from north, if you look at the increasing distance from this focal point, further and further away, you see very good agreement with exponential decrease of positivity as you go further and further away. So I go again over here. So you have north, that's somewhere in Poland, and you're looking at Slovakia from Poland, and you're looking at these annual regions, and you see the exponential decay of positivity as you go further. And that's the average positivity, so it's not influenced by the number of tests. So this some way says that there are some spatial exponential trends in the data. That, of course, explains immediately why you see this exponential distribution in individual municipalities. Is in agreement with that. Of course, doesn't explain it completely, but it says that, that's, if you're looking for spatial models, you rather have some exponential decay around, the peaks and so on, and longer scales, because otherwise you're probably not going to match the data. Because this is as close as you can get to the spatial data. Getting more resolution, where 60% of people were tested over one weekend, very hard to get, better data than that. Of course, you don't see it from all the points. You see it in this direction from north to south. So these are all three, pictures on the top agree. The ones in the center, they have some problem. I will explain in a second. But the south, you see similar, red and blue show actually similar patterns. So from central, if you make the concentric circle or annual regions from center, okay, they don't have nice features because you're somewhere going the wrong way. The circles are averaging the situation in the east and the west, so that's some way more complicated, and it doesn't show up on that. So the convolution you're some way making in those data, that doesn't work that well. So these are the exponential trends and the characteristic scale. And the last thing I want to say, lesson 3 is about the late epidemic. If you're thinking about what I was showing you, first was the early epidemic, looking at how wave look like. Second one was showing you like the middle of the epidemics, you're expecting this exponential trends. But now I'm actually interested in the late epidemic dynamics. And what can you tell? And I will look at the network models now, and I will show you that herd immunity is a questionable concept in that case. So first of all, the herd immunity is something, people tell us that if 90% of people will get infected or vaccinated, then it will be over and they will protect the rest. This is a consequence of a typical SIR type of model, and not only that, even if you're using stochastic models, they predict the same value of the threshold, 1 minus 1 over a reproduction number, basic reproduction number, and it gives you some intervals. Of course, now we're thinking about delta, so it would be probably require probably 90% of population to be immunized. But doesn't work that way. If you look at UK, UK had on August 26th, they had 93% prevalence of the antibodies. It was 6 weeks ago, and the 6 weeks ago they have 30,000 cases each day, and they have a couple thousand people in the hospital still. So what I'm some way saying, it's not working exactly that way. Even 93% do not work. Of course, there's a partial protection by the vaccine. There may be some other arguments that the level would be higher, but it seems that it doesn't give you a completely right perspective. Anyway, so let's look at the other model, and I will talk about the spreading on the networks. So some countries actually provided data, like Singapore, which early in the pandemic was showing exactly how the cluster looked like. So this is a picture. It's amazing data, and they show you the details. You can check, where it happens and who infected who. Amazing graphs. Anyway, so but you also know some cases. This is a special case you probably are familiar with. This was the Rose Garden in White House, and there was this one super spreader. We don't know who was it, but this is pretty well monitored, and you probably remember it in US. It was a kind of event. They also were testing by antigen testing. Everybody was negative because before the event. Anyway, so I will look. I will look at the problem from the perspective of a mathematical model, and it will be so-called configuration model, which actually is a graph model on which you prescribe node degrees. So you some way you say how the degrees of the nodes are distributed in the graph in some kind of random graphs, and in this configuration model, the graph is created that each graph you make these half edges and then you connect them randomly. So you will have random connection of half edges. You may have eventual double edges and self loops, but they are very marginal. You don't care about them. And you can introduce different types of distribution of degree nodes. So one of them is Poisson distribution. And if the degrees are Poisson distributed, then you recreate the random graph. If you use the parallel distribution, then you actually get interesting cases which are in agreement with real social networks. You can get something which is very similar to scale-free networks. So in this problem, you can look at the percolation. So we're thinking now about this vaccination process or immunization process. When first you have the full graph, and then you start to eliminate the nodes. with some high probability. So first of all, the picture in the left is phi equal 1. The second one is phi equal 0.7. So 30% of the nodes are some way discarded, and you just get the remaining edge, remaining nodes and edges. And 0.3 means you leave only 30% of the nodes, and phi equals 0, you completely some way everybody is immunized and nothing is happening. So, and you're looking what happens with the graph. So you may think about this graph is a graph of social network of people, it's static, it doesn't change. Of course, that's an assumption, which is not valid for sure, but it's a static network, and you're looking, what happens with this network. Mark Newman from University of Michigan has a lot of, has a textbook written on this subject, which is beautiful. And also he had a lot of work in this related area. So if you look at the Poisson distribution, so that's a random graph, you see exactly what you some way want to see with the herd immunity. So when you're vaccinating, and on the horizontal edge is this transmission probability. So it means vaccination. If you vaccinate more and more, you go to the left. And it shows you the size of this large cluster. There's one large cluster in the network, and it shows you how the size of large cluster in the limit of a high level of large number of nodes, how it looks like. So and it seems that if you reach this epidemic threshold, which is for this Poisson distribution 1/c, where c is the parameter, this decay parameter, then you reach this herd immunity as well, because then you have a 0 probability some way of the large outbreak afterward from single introduction of the disease. And you can calculate some way the advantage of this configuration model is that it provides you tools to calculate almost everything. Anything you can calculate, you can. It's a beautiful combinatorial tool, and I really enjoy it. So so this shows you that for random graphs, there is some hope for this herd immunity. For finite networks, the corner some way is not so sharp. If you use it numerically, you see it's a little bit smoother, and okay, then it's a little bit further, but still fine. So these are on the real networks, and if you do it on real networks, you see on the power grid, if you randomly eliminate the nodes, the power grid has the similar feature, the road network as well. But power grid and road network are planar networks. So they are 2D networks, not exactly the social network of people. So if you're looking at social network or internet, oh man, there's no transition. There's no herd immunity. So that's a really bad news to some extent. And it's really, one can show mathematically that if you have a power law distribution of the degrees of the nodes, then really there's no transition, and this critical threshold is at 0. But of course, look, this is the probability. So how many nodes are away? So, and this is the size of this giant cluster. There's this giant cluster, Percolation cluster, which is there. But you see, there are many more nodes which are somewhere in between. So there is this giant cluster, but in networks with say 5 million people, or Slovakia 5.5, maybe there's a hope. Maybe the hope is that, okay, giant cluster is there still, but if you vaccinate 70% of population, the giant cluster is rather small, and the rest maybe is uninteresting. So we want to see what is the uninteresting part, and that was the last part. And here's the picture, which always shows you what the uninteresting part is. You have a giant cluster, and you see how the remaining clusters look like. And you see they are really small. There's not that there's another big one and so on. They are really small, and most of them have a structure as a tree. And we actually look at it numerically whether this is true. So there's one more node which actually the last, this is good news. The good news is that everything you've seen so far was randomly eliminating the nodes, randomly eliminating the nodes. But okay, that may be the case in vaccination. But if there was a previous wave, the people with most contacts get most likely getting infected. So in that case, actually, you don't need that many nodes to get eliminated. And it's amazing that for power law distribution with the degree 2.5, actually you'd need to eliminate only like 5% of the edges of the nodes, and you will have the herd immunity. So herd immunity is very easy to achieve once you eliminate super spreaders. But potentially right now, super spreader is every kid in a school. So that's really complicated, and you cannot do it. So, okay, this helps maybe for the adult population to some extent, but for the kids, unvaccinated, and those who spend time home too much instead of school, okay, it doesn't work that well. So I bet it's a good news. And it's true for all the networks, even for real networks. In the social networks, if you eliminate about 30% of nodes, immediately, with the highest degree, the social network just decomposes into small components. Okay, anyway, so but we were looking at the other components beyond giant, and this is going to be really, really short now. It's some way show you that and if you rescale it, and this is the picture when it shows you the rescale number of components, the number of components that if you vaccinating, and the vaccination now goes forward from 100 to 0, so that means percentage of nodes remaining. So if you're vaccinating more and more, or immunizing more and more, the number of components is actually growing, and by component is also a removed mode. Of course, node is also considered as a component. Then it has this shape. And you can prove that this scaling works very well. Also, you may look at the component sizes, how the component sizes show up, show scale with the number of components, and you see some algebraic trends. There are two phases, and with two different slopes. And there's a similar work of about the fragmentation of random trees by Eli Ben-Naim and Zoe Kollár, and they show that on random trees, if you're eliminating the nodes, you also see algebraic trends. They proved it by some really nice calculation. And this is the picture when 50% of nodes are removed, and they're looking how the individual components are distributed, the component size and relative frequency. And they see this algebraic decay, cubic algebraic decay mostly, and then some tail. And we see very similar behavior, in our problem. So we didn't prove it yet, but seems like it should go along the same way. And the last thing I want to show you that how the small components, how they look like. This is for small graph, but just 250 nodes. So this is a pretty small one. And the sizes of individual components, actually, they follow logistic trends. And that's there's a really strong agreement with logistic curves over there. So the individual sizes of small components are going down logistically. But we also look at the fragmentation rates, how the small components were fragmented. And we show numerically that the small components, they behave as trees and stars. And here's the really important thing. So that some way answers the Bernard question, why it's easy now to teach on campus, although there's no herd immunity. And this picture some way shows the whole story. Yeah, the giant cluster is already too small. Okay, that's you may be unlucky that you are part of it, but the giant cluster is small because you have said 97% of vaccinated. Okay, giant component is small. What about the other components? And if you look at them, what you see is they typically have this star shape or the tree shape. Okay, they are cycles, but not that many. So it some way says saying that what happens, typically you will see super spreading events. One person infects all the others, in between this graph, but it doesn't go any further. So what you see is that one person may infect many others, maybe 10, 20, even it's possible, but they do not infect the others. This is just coming from the graph theory, from the decomposition of these configuration models graphs. So that's some way amazing idea you may get just from looking really at the random graphs and percolation properties. And for me, this is really shocking that you can get such an easy conclusion out of this. Anyway, so 3 lessons, but now looking, from different perspective, what I have learned over the last year is that in real time, you don't have time to really develop like really hard theories and so on. Simple observation matter most. And often you can in some way translate them into policies and so on. So really simple observation matters most. Model selection must be very wide and open. As you see, I showed you 3 really different perspectives on the problems. One of them was looking at the data and fitting the data by some ansatz. The second was really looking at some statistical properties of the data. The third one was models on percolation on graphs. Okay, so very different perspectives and very different types of models. And the last lesson I learned was that even a good result may not help at the end. It means you may try to communicate whatever to the politicians and policymakers. They sometimes do not care. They think they know better. So with that, I'm gonna finish now, and yeah, that's it.